first, I'd like to say good morning and thanks a lot for inviting me. Yeah, I would present results from 3 different groups. I work together with Samsa Koponen from Psyke and also Petra Philipsson from Brockman Geomatic AB Sweden. So my presentation is here's an overview. So what I want to talk about is what we did in terms of biooptical and remote sensing work. I work mostly in biooptics, and I show you some results from joint cruises that I did with Umeå University, where we mostly did intercomparison of optical methods. And then I also show some results of the development of a new algorithm to derive inorganic matter from space, and then how we work with the validation of Sentinel-2 and Sentinel-3 data, satellite data with different spatial resolution. And I will show you some examples of time series derived from satellite that show the high measurement frequency of satellite data. And I will then summarize the results and show an outlook of later work. So our task was mostly to map the Bothnian Bay, but of course remote sensing covers large areas, so we could also do the Bothnian Sea. And the main reason is to monitor the pressures, human pressures on water quality, and also to provide input data for habitat models. So the data we have been using is Sentinel-2 data from the ESA Copernicus program, which has 10 to 60 meter resolution. And from this data we can derive all optical parameters. Actually, I listed them down here because this is an ocean color Sentinel-3. So these are the optical parameters: chlorophyll A, Secchi depth, turbidity, and also yellow substance that's also called colored dissolved organic matter. So the Sentinel-3 data is actually the ocean color data, has a 300 meter resolution. And these are called moderate resolution maps. The aim of the biooptical work that I was doing was mostly to characterize the Bothnian Bay and also the Bothnian Sea optically, to set up common standards and protocols for the optical measurements at sea, and also to work with the description of the errors involved, because we need good quality data for validation, and then to evaluate satellite products and also to model reflectance based on the biooptical data that I was measuring. So why should it be important to do optical measurements? Of course, you know that light is one of the limiting factors for primary production, and color dissolved organic matter, or basically yellow substances, they're very, very high in the Bothnian Bay, and they limit the productivity. So we also could show that color dissolved organic matter favors bacterial production, whilst the primary production in the upper estuary is limited by color dissolved organic matter. It is also likely that inorganic suspended matter plays a strong role in the light limitation, because there are very high concentrations of inorganic matter close to the shore. Generally, there's very little optical data available from the Bothnian Sea, so this is what we're contributing with in this project. So here first a little bit about the error statistics. Chlorophyll A usually has an error of 7 to 10% if you measure it with a spectrophotometer. And suspended particulate matter has an error of about 10 to 13%. It depends on the ranges of values. And turbidity 10 to 12%, and color dissolved organic matter, a yellow substance, is about 3 to 6%. So you can assess your data quality by first looking at those standard errors of the mean, which will basically give you an idea if you're doing a good job with your measurements. So what I've been doing was working together with Umeå University, and we used the research vessel from the Swedish Coast Guards, the Maritime Administration, and we did several cruises in the Gulf of Bosnia. We started here, Umeå, went first down and into the Bosnian Sea and then up into the Bosnian Bay, and had some additional stations that were especially added for this SIMBOS project. They were in rather shallow areas, so we had to use a small boat for that. So the key results that we got in terms of assessment and comparison of methods between Stockholm University and Umeå University, we found that there were clear differences in the turbidity measurements, and then we introduced joint measurement protocols. We also saw that the Secchi depth is measured in different ways. So the international standard is 30 centimeters. Umeå uses 20 centimeter diameter, and I think HELCOM 25 centimeters. So it's different to the international standards, but we didn't find any significant differences. Then color dissolved organic matter is usually filtered with glassware, but because of the time restrictions, the monitoring groups use plastic syringes, and they of course can produce color dissolved organic matter. So our recommendation is not to use these. Then also we found that chlorophyll A by HELCOM combine is actually different to an international standards. Again, we would like to invite people to look at that and see how they can improve the chlorophyll measurements, because it's likely that there is a systematic underestimation of chlorophyll. Yeah, and then we sort of would like to request the providers that they evaluate their errors and provide that also with the measurements. Yeah, and we provided optical protocols to SIMBOS, so if anybody wants them, they can be provided. So the idea of what we do in remote sensing is we use the remote sensing reflectance that we measure from space, and from that we can derive information about these key optical properties. One can also use near-infrared to derive information about sea surface temperature, and then all these different sort of large-scale processes that again affect the optical properties. So these are humic substances and algobiomas are derived from the absorption that is derived from the reflectance. And so A is absorption, B is scatter, and scatter gives us information about the turbidity. So suspended particulate matter. And all of these, they influence the Secchi depth, which again influences the growth depth of macroalgae and seagrass, and they also limit primary production of the phytoplankton, and the SPM may also affect fish behavior. So we can get quite some information just using satellite data. So we measured also the reflectance at sea. I used a radiometer, and basically what we saw is that the satellite overestimates the reflectance, but the reflectance spectrum was quite okay. Then we also used the spectrum, the optical measurements to simulate the spectra using radiative transfer modeling, and you can see with the SIMBOS specifications, we actually got a quite good reflectance spectrum. We measured absorption and scatter with this AC9 and also suspended particulate matter, and could derive the inorganic fraction from that. And from the relationship between the two, we could then define an algorithm for inorganic matter that we applied here to a satellite image from April. a composite image, and you can see where there's the highest influence from coastal processes and coastal erosion. Then we also used monitoring data for the validation of satellite data. So you can see there are quite many monitoring stations that were from the SeaMOS project. And then here, this is a turbidity map that was produced by Syke. And here you see an event where there was high wind. Then you get a lot of wind wave stirring and resuspension of sediments, especially in the shallow areas. Here, this to the right, this is without strong winds. You can see here that the coastal runoff in the turbidity. Here you can also extract time series from, this is from a station. From this station, there's a time series extracted. So this is from Sentinel-2 data with 10-meter resolution. And you can here see that the satellite data gives you much more detailed information about the seasonal changes. So the MS, this is the measured data in situ measurements that misses sort of some of the key events here because it's just not frequent enough. Then you can also see effects of dredging in the Sentinel-3 image. Sentinel-2, sorry, and here just coastal runoff in the different estuaries. And the data is accessible on the Targa service from Syke. And Bokma Geomatic AB, they work with Sentinel-3 data, 300-meter resolution. Here we have also turbidity. We have two Sentinel-3 satellites in space. So here you see two images with 1 hour difference. You can see that it changes a little bit over time. So this is also where satellite data gives you additional information about dynamics. And here you have chlorophyll A derived from Sentinel-3 data as well. So here that's a station in the Roneo area, and that's the time series, that's the full Sentinel mission data from early 2016 to end 2019. You see that the satellite data gives you much more detailed information. These again are the measured data points, which are quite few in comparison to the satellite data. So this is from one single station. Here's a shorter time series, and you see how the chlorophyll changes. Here's an example of SETI depth derived from Sentinel-3, same date, and CDOM. I would like to point out that CDOM is inversely correlated, so color dissolved organic matter is inversely correlated to salinity, so this may also help you to define where your estuary starts and where it ends, this type of data. So we found there's a great need to compare the measurements because there can be quite a lot of differences between groups. So we need error characterization and also joint measurement campaigns. And the Swedish Agency for Administration for Water, Swedish Marine Administration for Water Management, yeah, something like that. They have given us support also to train the Swedish monitoring groups now in 2020. And we could also offer the same support to Finnish groups in the coming years. The satellite data derives time series with much better temporal and spatial resolution. Many features are actually missed with standard monitoring data, for example, upwelling events or algal bloom events. We got very good results for chlorophyll A, SETI depth, and CDOM using Sentinel-3. And for Sentinel-2, we use at the moment mostly turbidity, derive mostly turbidity, but we can also derive the other components, but we need to do more research to improve the products. And we produce this novel algorithm for inorganic matter. The future plans, we really want that the optical protocols are followed by the providers and that they provide the error measures, error information about their measurements. And that they describe the uncertainties in their data, because only if we have very good in situ data, we can also improve the quality of the satellite data. And we need more inherent optical property data, so these are absorption and scattering, to improve the models. Yeah, and the Copernicus mission is still at a very early stage, so we expect quite an improvement of the products in the coming years. And there's a continuous need for validation, and we need to do further work on integrating satellite data into oceanographic models. So here we can, for example, use turbidity as an input, as a driver for models. And we can also use Secchi depth as a driver, because it shows us the light conditions and has an influence on the productivity. And we can also use chlorophyll A maps to test the models. Yes, thanks. Sorry, I went a bit over time.